Great. Well, good afternoon. Thanks everyone for joining our virtual discussion today. This is a topic that I'm really excited about and frankly hasn't gotten enough attention in Washington, D.C., but it's a really big deal. And that's the Frontier supercomputer shattering the exascale barrier, entering the pole position on the top 500 and the green 500, two indications of supercomputer performance. I'm John Hoganson, Corporate Vice President at AMD, but more importantly for today's discussion, I'm co-chair of the Task Force on American Innovation. Task Force on American Innovation is a coalition of businesses, trade groups, scientific and engineering societies, and university organizations supporting the federally funded U.S. and science and technology research enterprise. It's the only science coalition that brings together industry, academia, professional society organizations for the purpose of funding advocacy, research funding advocacy on the Hill and in the administration. We're thrilled to host today's discussion because it's a perfect example of why this coalition exists and what we're trying to do to really improve the research and innovation atmosphere in the United States. A quick note on our format today. We're going to be joined by, we believe, two congressmen. I say we believe, Congressman Fleischman and Foster. They are in the middle of votes right now. Anyone that has been involved in Capitol Hill knows that sometimes things get preempted. So we're hopeful that we will have the two attendees will do some initial opening remarks. They're both co-chairs of the National Labs Caucus and huge supporters of this project and the research endeavors as a whole of the U.S. government. Then we'll move on to a panel discussion. We have a great panel for you today. If we have time, we'll then move on to a Q&A from the attendees that are out there. One quick note on the questions. If you do have a question, please post that to the Q&A section on your screen and not the chat section. We're going to monitor the Q&A section and not the chat section. The chat goes to everybody. Q&A is where we get the questions from overall. So address theirs there. So with that, let me do a quick round of introductions, and then we can move into the overall program. As I mentioned already, I'm not sure they've had a chance to join. We have Representative Foster and Fleischman will be joining us hopefully here soon. Representative Foster represents Illinois' 11th congressional district and has served in Congress since 2008. He's an actual physicist, which may help him or hurt him in Congress. I'm not totally sure, but it does mean that he truly understands the importance of the research enterprise in the U.S. and federal investments there. Representative Fleischman represents Tennessee's 3rd congressional district. He's an appropriator, but more importantly, his district contains Oak Ridge National Lab, so he's really a proud papa today to see the success of the Frontier supercomputer overall. And then our overall panel discussion, we have 3 distinguished guests. Doug Kofi is, I'm trying to get the whole title right, so jump in, Doug, if I get it wrong. Associate Laboratory Director, Computing and Computational Sciences Directorate, and Director, Exascale Computing Project at Oak Ridge National Laboratory.
You got it, John. Thanks.
Excellent. Let's get my notes here. But most importantly for this, he's the crucial link that pulls together all aspects of the successful project. Without Doug, we may not all be here. So it's really important that he's here. He's been at Oak Ridge since 2006. He has a doctorate in nuclear engineering from Purdue. Ron Bertois is Director of Leadership Computing at Hewlett-Packard Enterprise. Prior to HPE, Ron served as CTO at the Department of Justice, and before that, CTO of NOAA. And finally, and near and dear to my heart as an AMDer, Mike Schulte, Senior Fellow for Silicon Engineering at AMD. He's AMD's lead on Frontier and El Capitan, which is actually another supercomputer we're building for the Department of Energy at Lawrence Livermore, and likely to discuss in the future. One divergence here, I just want to say that I was hoping to be able to say that, and Ron doesn't know this, he kind of messed up one of my talking points. I was going to say that everyone on the panel and the discussion had Midwestern roots. I'm from Chicago. Bill Foster is from, represents the Chicago area. Representative Fleischman went to the University of Illinois. Doug was in Missouri and Purdue. Mike Schulte is from Wisconsin and was a professor up there. But Ron, in doing your research, I think you're from the East Coast. So,
Philadelphia and Villanova. So
there we go. Okay, somewhat closer to the Midwest. But anyway, that was my one Midwestern heartland talking point I was going to talk about, but that's okay. So, all right. Well, with that, I think we can kind of transition into our overall discussion. I don't know if either of the congressmen have been able to join yet. So we will kind of just go with the flow as of right now, if that works for everyone and for our panelists. And I guess we can kind of just jump into our overall discussion if that works for everyone. And maybe, Doug, I will sort of lean on you to start, kind of give us a little bit of background on the Exascale program, why it's so important, what some of the goals were, and maybe a little bit of the history too. I know it was a 10+ year endeavor to get here, and why it's been such a big success. So, ultimately, what is the Exascale program? Why does a nation need it? And what are really some of the potential outcomes and benefits for us?
Sure, Don, thanks. So we've been talking about Exascale really since 2009, and really trying to understand what could we do with technology like this for the nation, the Department of Energy, et cetera. But I'll talk a little bit about ECP, Exascale Computing Project. It's a part of an overall Department of Energy Exascale Computing Initiative. It's a joint effort by the Department of Energy Office of Science and National Nuclear Security Administration. ECI, the overall initiative, really includes the ECP project, as well as procurement of the first 3 Exascale systems, of course, Frontier here at Oak Ridge, Aurora at Argonne, and El Capitan at Livermore. It's really focused on the delivery of an enduring, capable Exascale computing capability for a wide range of applications. ECP, again, a key part of ECI is the vision. I think we're achieving it, frankly, is accelerating innovation with Exascale simulation and data science solutions that enhance U.S. economic competitiveness, and including quality of life, strengthen our national security. ECP has 3 basic thrust areas. The first is deliver Exascale-ready applications and solutions that address currently intractable problems of national interest, create and deploy an expanded and vertically integrated software stack based on Department of Energy, Exascale, and pre-Exascale system activities, leverage U.S. HPC vendor R&D activities, of course, such as HPE and AMD, and ultimately enable future U.S., I would say, revolutions in technology development, energy, national security, scientific discovery, economic security, and healthcare. Just a little bit more about ECP, then I'll turn it back to you, John. ECP is a 7-year large R&D effort. We've been ongoing since 2016. Leaders from 6 Department of Energy national labs lead the project, but we have 15 of the 17 DOE labs engaged in technical work, along with over 90 universities and almost 100 companies in the U.S. So approximately 1,000 researchers distributed across over 80 R&D teams. The potential outcomes and impacts, I believe we're at the crux of realizing them. Well, I think we'll be far-reaching for decades to come, based on how Exascale applications will be able to be more predictive and consequential than ever before. One way to think about them is virtual time machines and digital twins that can reliably ask and answer what-if questions both now and in the future. Questions relate to problems, like I said, of national interest, including national security, energy security, economic security, scientific healthcare, scientific discovery, and healthcare. Really, essentially, societal and quality of life issues. The applications will also incorporate, where possible and appropriate, AI and machine learning techniques to further augment and accelerate the workflows. It's really a once in a career, once in a lifetime opportunity for our best and brightest in the nation, John. And we're really, really excited to be here and share kind of where we are and what we anticipate in the months to come, frankly.
Thank you. So it really is getting to the Exascale level, to this benchmark, really is a huge success. And not to steal Mike's thunder a little bit, but from the AMD perspective, one of the things that's great is this the public-private partnership here. And it really is a great model of how, when government, industry, and academia can come together and work, it can be a huge success. So let me, I guess, throw out the next question to both Ron, you, and Mike. And really, what is the value of the public-private partnership in ensuring the U.S. continues to lead the world in advanced technology? How can AMD, HPE, and Oak Ridge collaborate on Frontier going forward? And maybe, Ron, you can just kind of start, and then maybe Mike, you can jump in and give your perspective about really the importance of that public-private partnership between HPE and government and partners with AMD.
First off, so this is a really exciting topic. And from a PPP perspective, let me just say that I think HPE has been really proud of the partnerships that they've been part of. As an example, I think the COVID-19 HPC consortium, we were one of the original founding members. And that was a partnership that was designed to bring together government, industry, and academia. And I think there was about 114 projects that we went through. So really proud of that type of work. Additionally, HPE joined other tech leaders and we pledged our patents to be freely used in support towards these initiatives. So these types of partnerships are really important, but I want to take a step back just from my time in government. When I was at NOAA, I was part of a large partnership that we pushed out. It was called the Big Data Project. It's a big success within NOAA today. The idea is that when NOAA creates its weather and climate products, it's using a tremendous amount of data. That data, once you get the results the government is looking for, it has its initial use. It has a lot of latent value to the overall arching market. That value we look to untap, really to release by partnering with a number of industry partners and academic partners to release out into the public to really foster innovation, spur new jobs, create new products, really outside of the scope of what the government was thinking about across this large weather climate community worldwide. And honestly, we had a huge amount of feedback from the American companies about the value of that data sets, and you're hearing a lot from the satellites. From my standpoint, inside of when you start seeing the excitement we have for the type of partnerships within HPE that you're seeing with partners like are here today in the Exascale projects, this tends to be the foundational work. We have a strong set of relationships that we build with partners. We are that looking to make the investments based upon the needs of our federal partners. You're seeing reuse of that technology that allows us to then work across industry and be that worldwide HPC leader. And you're also seeing transitions of this technology out into industry. So we're seeing there was we saw the blast codes that we saw out of the national labs get shared out through some American companies, and you're seeing it in drop tests for iPhones and for planes and cars that affect our everyday lives. You're seeing some and other federal agencies that we are releasing the codes, and you're seeing the impact of structural analysis, where you can actually imagine what the object looks like. You know where the rivets are going. You can look where the landing gear is going. These innovations not only drive our HPE products, but they also drive innovations that get transferred out into industry. And from our standpoint, this becomes a foundation of our product lines that help us drive down the cost for supercomputing for federal agencies, push forward those missions, and allow us to be that worldwide leader for American products and leading high performance computing. Mike?
Yeah, thanks, Ryan. Thanks, John. Yeah, also very excited to be part of this panel and very excited to be, part of the whole Exascale computing project and frontier effort. Regarding the public-private partnerships, these are really very essential in terms of maintaining U.S. leadership. The technologies that get produced, from these partnerships, whether they're for high-performance computing or artificial intelligence, they really allow the United States to remain at the forefront of leading technologies and really having breakthroughs not only in the technologies that are used to build supercomputers, but also in things like design, manufacturing, scientific computing, et cetera. The other key thing is that the technologies that are enabled through these partnerships really allow critical breakthroughs in both scientific discovery and medical breakthroughs. In addition to that, they're incredibly important for creating new jobs. They allow new technologies to come out that the United States is a leader in. And also they really help to both increase the security and the prosperity of our country by doing things like helping us to better protect our nuclear stockpile and helping to create new and innovative technologies. Now, one of the really great examples of the public-private partnership is Frontier. Now, with Frontier being the world's fastest and most power efficient supercomputer, it's very excited. And this was enabled by the Department of Energy private-public partnership that Doug talked about earlier that started back in 2009. Through this partnership, AMD and HP and other institutions, along with the DOE national labs, were able to work together very closely on co-design to determine not only what are the right technologies needed for exascale computing, but also what technologies are needed to propel the high-performance computing industry forward, and really prepare us for the next wave of exascale. These technologies were really essential because they not only provided technologies that went into high-performance computing systems, but they also led to advances in both hardware and software that are used in other products, such as laptops, desktops, data centers, to really make them faster and more power efficient.
Great, that's super helpful. And actually, Mike, that was sort of my next question, and so maybe you can just elaborate a little bit too. Is some of the key features around the AMD hardware and software that are used in Frontier. What makes that unique? Why was that? What were the challenges there in getting those together? But I think some of those key features would be interesting to kind of highlight.
Yeah, thanks a lot, John. So fundamentally, AMD provides both the processors and the accelerators that are used in Frontier. So these are the key computer chips that allow us to attain very high performance and high power efficiency, and really what ended up helping to make, along with HP's contributions, Frontier the world's fastest and most power efficient computer. The chips themselves end up leveraging the same basic technologies as what we use in, say, laptops, desktops, et cetera. But what we did is we made enhancements to them in order to allow them to be, very highly efficient for high performance computing, scientific calculations, artificial intelligence, and data analytics. So really optimized for those key applications. And then the chips have also been designed to make sure that they're very reliable and energy efficient, because when you're trying to do these calculations, one of the key things to drive is continued improvements in power efficiency. On the software side, the software used for Frontier is really designed to run very effectively on AMD processors and our accelerators. The software is open source, and that's very beneficial because it allows people from AMD, HPE, Oak Ridge National Labs, et cetera, to all work together to develop the software. And as Doug talked about, there's over 1,000 different scientists and engineers that are working on the Exascale computing project. This allows different people to contribute to that software and make it better. And similar to the hardware, the software is also used in laptops, desktops, game consoles, data center products, so a variety of other products that end up being sold by AMD.
Right. Really interesting. Thank you. So, Doug, let me turn back to you a little bit. One of the things we talked about is that this is, the fastest machine in the world, the top 500 list, Green 500 most efficient machine. So it's a really fast computer, but it's really more than that, isn't it? Right. So maybe you can touch on why this is more an achievement than really just building a dragster, right? There's a lot more to this than just a really fast machine.
Yeah, John, it's nice to have fast, but that was really not the end game. It was a result of specific requirements needed to develop timely and high confidence solutions to problems of national interest. So, when we talk about exascale hardware, we're not just talking about 10 to the 18 arithmetic operations per second. That's incredible. But we also need lots of memory, 10 to 16 bytes on Frontier, and lots of storage, again, kind of order 10 to the 18 bytes. So imagine, a whole bunch of zeros. This combination really of memory and storage and compute makes for the powerful ability to deliver what we call high science work rates, extremely high science work rates. So the rate of delivering extremely high science solutions per second. In other words, we can have high confidence, high consequence exascale solutions. And in other words, deliver better science faster. Lots of memory, lots of compute enable that. So we talk a little bit about what that means. We're using the age-old scientific method, hypothesize, test, analyze, with our exascale applications. So imagine if the science solutions were so complex they wouldn't fit into memory or took weeks or months or years to compute the solution. This would mean we either couldn't effectively utilize that application. In other words, it doesn't intersect any relevant design cycle, or we'd have to dumb down the application, make more approximations, omit some phenomena from the simulation. Now the solutions are at the point to where they're not reliable to make high consequence solutions and match experimental data. But with Exascale, we can really deliver high consequence solutions with, essentially uncertainties that are very low and quantified, and be able to deliver to our, stakeholders and decision makers, solutions that we can bank on. Exascale itself amounts to an entire ecosystem. Mike talked about this incredible hardware, 74 racks in Frontier. You need fast data connections between the nodes, the interconnect. You need a data center. You need data center infrastructure, space, power, cooling. You need the operating system, which think of it as iOS of your iPhone. The DOE software stack we developed is called the Exascale Scientific Software Stack. So think of those as SDK, software development kits. It's the kinds of things ECP has delivered. And then the applications themselves, which I'll hopefully be able to address here in just a few minutes. So think of that as the app store for the nation. And don't forget, we have expert staff and workforce from all domains and diverse backgrounds and points of view, the sort of thousands of scientists and researchers we've engaged. And frankly, ECP is delivering and deploying those tools on Frontier as we speak. So this is a very exciting time.
That's great. That's great. Well, you mentioned, Doug, we're going a little out of order, but you asked about talking about some of the applications. Why don't we go ahead and talk a little bit about some of those applications? What are exactly the Exascale applications? And you mentioned the extreme scale software stack. How do we, what does that actually do, and how do we support those applications?
So the applications we have are 24 first mover applications that span the Department of Energy mission space. Frankly, there'll be, I think, hundreds of applications that follow. But our applications span energy production, wind energy, nuclear energy, fossil energy, fusion energy, to energy transmission, being able to simulate the entire interconnect for our nation, fundamental science, nuclear physics, the strong forces in the universe, the origin of the universe, the origin of elements in the universe. Also, we've engaged 3D printing, additive manufacturing, trying to design new catalysts and new materials for energy applications, quantum materials for quantum computers, quantum interconnects, astrophysics, again, fundamental science, being able to understand how to risk assess for earthquakes, simulating the Earth system for climate science, cancer research, machine learning for precision medicine for oncology, metagenomics, being able to get understand more of the data that comes out of the Department of Energy light sources, and also national security, being able to be part of the assurance of our stockpile. So the applications span an incredible rich portfolio. And also say that these aren't boutique applications that are designed for one problem on an Exascale system. The applications are being designed to deliver science and engineering solutions from laptop all the way up to Frontier, El Capitan, Aurora. So I truly believe, John, that these are going to be our science and engineering tools for the nation for decades to come. So I'm very excited to be able to see these applications deliver on their promise.
That's great. That's great. Ron, let me put you on the spot a little bit, given your experience at NOAA. I know it was many years ago too, but I wonder, thinking about back to that experience, what would it mean to have access to this type of, power or computability now, given a role at NOAA overall? What does that mean to weather, climate change, et cetera? And then also kind of thinking about, as we're moving into a post-Exascale era, why it's important for Congress to continue to fund supercomputing programs. So, what are the benefits to agencies like NOAA? And just based on your experience, how could you have benefited? But then also, why do we need to continue to think about this, going forward?
No, it's a great question. And first off, I'd say that the way that Doug is characterizing these problems, it's an excellent overview. So from my standpoint, the federal missions, all of them, right, across the board, we have a requirement to have the ability to stay ahead of the requirements, or really the expectations of the American people, and ahead of our adversaries. We have to drive forward those national initiatives. We have to keep pace with American innovation. There is an expectation that the American government is going to push that envelope. Supercomputers are more than a tool, though, right? It's an advantage. It reduces the time to insight. It aids in our scientific discovery. It delivers on the operational capabilities that we have to deliver for the nation. And Doug touched so many of those. I mean, it's hard not to talk about this and then think about the Webb telescope, and congratulations to NASA. If there's anyone out there supporting NASA today, you look at those images and the exploration of those images, the advancement of the building of those satellites. There is a lot of dependencies from the exploration of the stars to the exploration of our oceans. It's a support, as Doug said, to the national security. It aids scientific discovery. Really, it really is the advancement of our research and insights through these tools. But I think you're talking about Frontier, and it represents a great partnership here today between the Department of Energy and Oak Ridge, and Doug's been a phenomenal advocate, AMD, and what HPE can do. And honestly, Exascale is a tremendous milestone. But I don't want to lose the fact that it's great that the thing that I think we're going to hear about is that Frontier is great, but what Doug is getting at is that Frontier is the foundation, and the science you're going to hear out of the Department of Energy across the country, and really from Oak Ridge, is going to be astounding. We can't wait to see what it is, Doug. And the reality is that in the post-exascale capabilities, this type of computing and leading up to exascale and post-exascale needs to be available inside of the agencies organically. They need to partner on the large problems with organizations like DOE, but the volumes of data that everybody is seeing across the federal government is really skyrocketing. The pace of innovation is relentless. The competition is fierce. Foreign nations are looking to make advances by investing into their versions of supercomputing. I mean, transparently, we know that China has 2 large supercomputers that are not listed in the top 500, and we don't know how big they are. Other countries aren't not waiting, and our missions need to be preeminent. In a world that's data-fueled, digital, our supercomputing capabilities will need to continue to advance. And I think some of the innovations that come out of this type of partnership, you think of the cooling envelope. People can't just buy supercomputers. There are limits that they're seeing inside of their existing infrastructure and facilities. The fact that this is the top supercomputer in the world and the top on the green, and you're seeing this extreme push towards reducing the amount of infrastructure you need to get this sort of peak performance is astounding. It's going to be important across all the federal agencies and to American companies. These US partnerships and this investment in large supercomputers need to stay strong for these federal missions. So I'm sidestepping the one question you had was, where were you going to see it? And I'd also say that, look, supercomputers in the operational world, in that weather world, and you asked me about it directly, we've just seen the operational supercomputers at NOAA just go live. It requires these extreme computing. The agencies require it, and all of this goes into, it's dovetailed together, John. Thank you.
Does it mean they're finally going to get the weather right, predictions right, so I can figure out when to bring an umbrella?
I like the uncertainty. I just carry the umbrella all the time. It's going to be
yeah. Well, it's fascinating because weather is one of these things I think we hear about every day, but you don't realize the complexity that goes around it, right? The modeling that goes into that. What you have to do to understand it. We watch the weather person on TV point to the pictures and those kind of things, and then it's wrong, right? And it's why didn't they get it right? Well, it's an incredibly complex system, and that's where we're building these machines is to kind of deal with that. So it's something we talk about a lot, at least is the importance of that model. So I want to go a little bit off. We touched on the Green 500 a little bit and the energy efficiency, but Mike or whoever, I wonder if you might talk about why that's important, the energy efficiency piece around this and hitting that benchmark, because there were really, and Doug, I think you touched on this in the beginning, there really were two benchmarks we're looking at, right? Which was the Exascale benchmark, but then also this 20 megawatts at an Exascale, and this machine is going to be a 1.5 Exascale machine, so 30 megawatts of power, so it keeps us in that range. Why does that matter? And by the way, 30 megawatts is still a lot of power, right? It's like that's still a lot of electricity. But why does that benchmark? Why do we really even care about that? So I don't know, Mike or Doug, if you want to jump in and kind of talk about that, I think that's an important point.
Yeah, I'm happy to talk about it a little bit. I'm sure Doug has further insights, but I think one of the key things is that if you look at the amount of power that's used by data centers, not only supercomputers but other computers, it's skyrocketing. People are using the data centers for doing cloud computing, for doing AI, et cetera, and it's really important to make sure that we're managing that amount of power before it gets out of control. One of the statistics is that if you look at for each megawatt of power that's used by these supercomputers, it costs $1 million. And so making these supercomputers as energy efficient as possible ends up being very important for the UX taxpayers. And then another key thing that kind of builds on what Ron was talking about earlier is if these supercomputers use tremendous amounts of power, then it becomes much more difficulty to build the facilities that are used to house them. And so given, available power in key areas, it was very important to come up with a highly efficient design where we could fit within the power envelope that labs like Oak Ridge National Labs had.
Yeah, that's great.
Yeah, I'll just add that a tremendous tool like this needs to be used, useful, and affordable. And part of the ECI initiative working with private industry was to make those three things a reality. And we're there. Basically, the goal was 20 megawatts per exaflop, and we're at about 15. And couldn't have done that without this joint partnership. So we were able to pull it off together.
That's one other, sort of off script question here then too. And maybe Ron or Doug, you can talk on this. The scale of this machine, you talk about the number of racks, Doug, but Mike, you also mentioned the power resources. What is the undertaking that goes into building something like this? It's not just, going to Home Depot and, plugging in some power strips. So.
Well, I've been around a long time, John, you can probably tell that. But basically what we've seen is incredible technology to where we have dense packaging, and the scale of this machine really isn't what I would have guessed. It's much more compact and small relative to past systems. Past systems, you might have 20, 30,000 nodes. Now you have kind of 9,400 nodes, and one node is incredibly powerful. 200 teraflops. That may not mean much to the folks here, but put 5 of those nodes together and you've got a petaflop. And one cabinet is almost 30 petaflops. So, the challenge really is to exploit the incredible power of one node. And so, if you've been around long enough, like I have, the sort of scale out, we're really now looking at really scaling in. And what's exciting is now on your desktop, you can probably have a petaflop. And so you can do tremendous science and engineering really with a few nodes of Frontier. So imagine now what you can do with 9,400 nodes. And, it's incredible technology and engineering to be able to pull off the packaging and the cooling, et cetera. I'm an application person, so I just get on and do what I want to do, but I'll defer to my colleagues here in terms of the technologies and how they've been able to do this incredible packaging of this compute power. And so it's been impressive to watch Frontier be assembled and right down the hall for me.
That's great. So, Ron, were you going to jump in, or Mike? Yeah.
I was just going to say, yeah, kind of building on that. So if you think about Frontier, there's over 150,000 individual processor chips, so both the processors and the accelerators, and then there's millions and millions of lines of application codes. And one of the key challenges here is to get those different computer chips and all of the code working together to really solve the problems. And so that, involves things like how do you get the different processors to communicate with each other? When the processors generate heat from dissipating power, how do you effectively cool those? So there's just a tremendous number of challenges. And that's why these US industry partnerships between the private and public sectors are so important. If you think back to Exascale, we started on this journey over 12 years ago, and we wouldn't have been able to bring together the innovation that resulted in Frontier if it had not been for these, long occurring partnerships.
I first off, I echo everything that Doug and Mike said. I mean, it's a great overview. I think I'm going to take this in a slightly different direction. The one thing I'm going to point out is DOE has this great vision, and you're hearing it, I think, in Mike's responses, but a lot of the work that we're putting in, it's really one of a kind. This is really cutting edge work. But with the encouragement and the partnership we're seeing with the federal government, it allows us to commoditize our approach. So you're seeing us not build a one-off for DOE, take that investment and run. You're seeing us put it into our product roadmaps. You're seeing our cooling technology show up in our supercomputing roadmaps. You're seeing the fact that we've built this giant fabric with DOE that is now becoming available for supercomputers for tomorrow. That fabric is that network in the background. The software libraries, the capabilities, you're seeing it from our partners with the processors. There's a tremendous amount of work, but we're also seeing the commoditization that is helping our company, our products, American companies use those products, drive down the cost, and really help other federal agencies make this type of technology accessible to them. So I agree with everyone saying, but I do want to point out that these aren't one-off, completely bespoke systems. They are cutting edge, they are first of a kind, but they really benefit the broader community.
Yeah, that's a great point, Ron. And the same thing with the AMD technologies, where we take, the same processors, the same accelerators, they're used widely in the data center. And then we take the same fundamental basic technologies and use them, throughout the product line. And I think that's one of the great benefits of these close partnerships, is it not only benefits the world's fastest computers, but it has much, much broader impacts.
Yeah, I think that's a super important point. And one of the things that I'm so excited about is, and I think that Ron, you touched on 2 points there. One, how unique this is in terms of cutting edge and all the work that went into this. I think we often hear that there are other systems out there, and this is just another fast one. But this really is a unique partnership, and the technology really is state of the art. And I think that point is lost a little bit. So I think it's great that you brought that on, Ron. But I think also, and certainly something that I like to point out when I'm talking to members in the Hill or others about this, is that the technologies that we're developing here, while it's state of the art, they're not necessarily one-offs, right? They're gonna make their way into products that are usable. Maybe not in my home computer tomorrow. Maybe it is. I don't know. Mike, you can answer that question probably. But soon, right? And that's really exciting. And if they're not making it into the home, they're certainly making it into the metaverse or wherever else that's out there. Other scientific research. So there's a lot of benefits that are out there overall. So I think that's great. Great point. So I actually think I was going to jump to some Q&A from the audience here, and I think it kind of touched on those, but I'll just ask the question again. Could the panel discuss the impact of Frontier on the broader U.S. compute ecosystem, not just the applications of Frontier, but how the technologies are advancing the overall broader U.S. compute ecosystem? I think we kind of touched on that, but I don't know if anyone else wants to add anything else to that overall. So.
Yeah, John, let me speak to the software aspects. So I mentioned one key product ECP has developed is called E4S, Extreme Scale Scientific Software Stack. E4S.io is where you can find it. It's open. Basically, it's about 100 software products. Think of these as libraries and components that you can leverage and build on for new applications. So what we've done there is we de-risked and demystified the complexity of hardware such as Frontier, so that it'll be much easier for people to onboard their applications. And so we're really excited about that development. We've been releasing this stack for about 3.5 years every quarter. So, and it's going to live on past ECP. So it's important for folks to know that one key enduring goal, and I think we're achieving that, is this sustainable ecosystem. And in particular on the software side of things, it was a once in a, frankly, career opportunity to be able to build this in a sustainable way. So I encourage folks who are interested to take a look. And, we do feel like that we're going to be able to onboard a lot of other applications. And NASA and NOAA have been mentioned. We're certainly reaching out to other agencies, NASA, NOAA, NSF, NIH, DOD. We are being aggressive in our outreach to industry as well. The companies that use applications, that develop applications. So part of our success is being able to make sure that this ecosystem is used and useful and sustainable.
Ron and Mike, let me ask the question a little bit differently, and I think you may have already addressed it a little bit, but I'll just ask it again. How does HPE and AMD benefit? How do your technology roadmaps? How do they benefit from being part of Frontier? So what are those things you're doing? I kind of know the answer, Mike, on our end, but on HPE side of things, how does being part of Frontier help improve HPE and help improve AMD and the products you're bringing to market?
So let me just, I do think we touched on this in the sense that the products you're seeing, from the cooling technologies, the networks, the engineering that we put into this, and the engineering we learn in coordination with our partnerships like AMD, and I'll let Mike touch on that. We do bake it back into our products. We do get a partnership ecosystem. You are seeing the reuse of this technology into the other products we're selling into other federal agencies and others. It does position us well to be a world leader. So just transparently, as someone who used to buy for the government and take care of some really important missions, both at Justice and NOAA, I would certainly say that knowing that we're not just buying a supercomputer, but the most capable tools for our missions is important to us. This is not an area we want to be second place. So we don't need our missions losing because we just don't have the tools in place for the great work that Doug and the other federal missions represent. Mike?
Yeah. So along the same lines within AMD, we really, both the research that was done prior to Frontier, as well as the development of Frontier, has been really critical to our overall roadmaps. We work very closely within the teams at AMD to make sure that we take the best technology. So for example, new techniques for doing power management, a lot of the software that was developed for Frontier and for the overall Exascale computing project in general. And we make sure that we drive those technologies into our future product roadmap. And just as Ron talked about earlier, we need to continue to have these investments in future supercomputers. We're taking a lot of the baseline work that we did as part of the key processors and accelerators for Frontier, and we're now building on them to enhance our roadmap even further for not only future supercomputers, but also future laptops, desktops, et cetera.
Great. We'll just take another question from our group here. Is there a supercomputer roadmap to coordinate industry? I think this is a question we get a lot, but is there sort of is there a roadmap? Is there some sort of thing that kind of defines the steps along the way? I don't know, Doug, if you want to start on that one, or
yeah, look, this is hard because it's such a fast changing field. But from the Department of Energy perspective, we are in the process of talking to a lot of vendors. There's an RFI out there right now asking a number of questions, really coming from the Department of Energy requirements, et cetera, for the next systems. And frankly, we're going to be putting together a revised roadmap before the end of the calendar year. And when I say we, it's a DOE National Labs and our Department of Energy sponsors, based on talking to dozens of vendors, certainly like AMD and HPE. And the roadmap will really be one that reflects Department of Energy mission requirements. Does it coordinate industry to the extent that we want to co-design and co-partner with industry to deliver on DOE mission. Yes. But it's really, there is a roadmap coming out from the DOE anyway that I think will, to some extent, answer that question. And it's a very important one and one that we're always working on.
I'll just add from the industry side, we take the information that we get from the DOE national labs and other agencies and use that to inform, what's the next area for research and advanced development that we need to be looking at in order to meet their overall goals and requirements. So for example, the RFI, that request for information that Doug just talked about, will be, providing input, but then also looking very closely at the requirements that come back from the labs and from other organizations, and really determining what are the key challenges that our chips need to be, our hardware and software need to be able to address in the future.
Yeah, and I think there's to pull on that thread from the HPE side, or really from my observation, there is a static roadmap from an HPE perspective, right? And I know you're talking about industry, but also from the federal government. One of the things I'd point out is the requirements. If you think of the coordination that Doug is talking about across DOE, that is hard. These mission requirements, they're moving aggressively. They have hard challenges in front of them. And one of the things that we are doing is that we have a baseline roadmap for the next couple of years, but we are working to make sure that we stay in partnership with the federal government and adapt our roadmaps to make sure that we can be that partner, which means our roadmaps are continuously, I don't want to make it sound like they're moving, but if you look at our long range roadmaps, we are designing to accommodate the requirements of the federal government and make sure that they're incorporated into our roadmaps for industry and coordinated.
And I'll add here, John, that for the next, think about out to 2035, the tipping points we're going to be seeing. It's incredible. We're going to be seeing more compute on the edge. We're going to see more intense integration of AI and machine learning. We're going to likely see quantum. And so this is going to be an exciting and challenging kind of 10 to 15 year run. It always has been, I think, in big compute, but we've got some exciting times ahead. So the roadmap needs to reflect those sorts of things.
Right. Well, just sort of, I'm going to sort of use part of a question we have, and that was, what is the task force? Does it give a specific ask for Congress in the future of funding for high performance computing? And, the task force overall supports all, research areas. So our ask would be, to continue to fund it. But I want to twist that a little bit into a question about, what's next. So we've hit, Exascale. Companies have talked about Zetascale. To be honest, I don't really even I can barely comprehend Exascale. Not sure what Zetascale looks like. But as we think about this, and Doug, you mentioned a little bit, AI and ML and all these quantum that are coming in here. And it's a little hard to obviously answer the question. But what do we think about next? And we don't just end here, right? So what is DOE thinking about? What is industry thinking about in terms of the next steps, the next goals that we're trying to reach? We're obviously not just going to all retire tomorrow, although that might be nice. But anyway,
So, John, if it's okay, I want to jump in here. So. Sure. I'm gonna go back to your first part, and I'd actually love to talk the technology side, but first thing I want to make sure that, from my standpoint, there seems to be two obvious places that I would hope Congress would get engaged. One, obviously there is the USICA and the competes legislation. We support it. There's a lot of good that can come for the nation and for our capabilities for attention to those bills. And then from the other side of that, I would also say that continue to support the federal missions and the leadership side of those federal missions for high performance computing. The Exascale, it wasn't a milestone that means that we've got there. It was an important milestone, period. And what you're going to see is that the advances in science, the advances to the missions, the capabilities that we need to see in high performance computing, you're going to see requests in Congress coming from these federal missions. They're important. And if you're having challenges, transparently, if you're having challenges understanding what that means from a technical perspective, I would encourage everyone, feel free to reach out to our teams. And I would say, I would hope that there will be support for this type of investment. Thank you, John.
Well, actually, I see that we've been joined by Congressman Fleischman. You missed, I introduced you earlier, Congressman, as the proud papa of the Frontier machine at Oak Ridge National Lab. I know you're just, you were all busy voting. Those of us that have been in DC for a while know that it can be unpredictable schedules and all those things. So thank you for joining us overall. I know you wanted to say a few words, so I thought I'd give you an opportunity to jump in now. And I thought Ron's pitch to continue to fund it, given your role in the appropriations, is a good segue there to transition over to you, Congressman. So I'll let you jump in for a few minutes here.
Well, thank you so much. This is really a privilege to be able to join you all today. Literally, we just left the floor of about a 19 vote session. Congressman Foster and I were both down there casting votes on the NDAA amendments. Thank you so very much. He and I work closely together on the National Labs Caucus. We love all of our national labs. Of course, I'm privileged to represent ORNL, Oak Ridge National Laboratory, which actually performs every function that a national lab can perform. We're very, very proud of that. We used to always lack one or two, but we've done exceedingly well. In my very brief time joining this conversation, as I say, just got off the floor, I have been so privileged over the years to vote for the advances in Exascale. Frontier is going to be outstanding. Obviously, when I came to Congress, we were #1 in the world about 12 years ago. We slipped to about #5. Now the United States is back in first. So critically important. But I want to thank each and every one of you all for your work and your advocacy. And as an appropriator, particularly on the Energy and Water Subcommittee of Appropriations, it's a privilege to advocate for the great things that all of our national labs do. So I thank you for your continued support. Please reach out to your members in the House, in the Senate. This should be bipartisan and bicameral. America is a better place when we fund the key missions of our national labs. And with that, I'll be glad to yield back.
All right, thank you. Well, I'll give back on the, and Doug, since you're Congressman here, opportunity to talk. We were talking about what was next on Exascale and going forward. I don't know if you wanted to add anything to that part of the conversation.
Yeah, you bet. So, we just don't go and do Zetascale because it's cool and that's the next thing. What really drives us is what problems can we solve now with Exascale. So I anticipate a intensive Exascale era science campaign with the applications that we have developed. We're going to onboard more and more applications. And so I think you're going to see some incredible solutions emanate from this technology. And I think you're going to see some incredible breakthroughs. So the first thing is we've made a heavy sort of sense of urgency push to develop the technologies. Now they're ready to be exercised on delivering solutions. The second thing is we're part of the roadmap is to understand what problems are not achievable or easily achieved with the current technologies, and what do we need to do next, and that'll be part of that roadmap. And so it's not just let's do quantum or AI for the sake of it, but where can those technologies, edge computing as well, deliver solutions that we can't easily obtain now. So I think next you're going to see in the roadmap some new requirements emanating, and this is sort of the fast moving pace of computing. So I think you're going to see these incredible science and engineering campaigns, and then roadmaps that are going to be another push for that next set of technologies that can be that can address solutions that even we can't address at Exascale.
Thank you.
And I'll just add to what Doug said, that as we continue to push technologies, we're able to solve more and more important problems. I mean, if you think of some of the biggest problems that the world is facing right now with things like global climate change, fairly rampant diseases, being able to, do very efficient manufacturing, coming up with new forms of renewable energy. These are problems that Exascale is going to be really, very, very important for, but these are challenges that are going to continue to grow over time. And for the US to continue to remain, highly competitive and really be able to come up with the next set of great solutions, we need to go, not beyond not only what we're doing for Exascale, but really driving the forefront of technology. And that's why these partnerships end up being so important.
Great. That's wonderful. Wonderful. Well, we only have a few minutes left. Let me end with sort of a provocative question, if you will. I think we often hear that, too often that the U.S. can't do big things anymore, that we're often falling behind in technology. But here's an example of where we are now number one, and it's a big successful challenge. It's been many years in the making. I think it's something that when it was started, and Doug, you can probably talk to this, 10 plus years ago, we weren't necessarily sure we could do it and hit the benchmarks that they were laying out. I think we did that. So Mike and Ron, maybe you could just touch on some of the challenges that your companies had to face in trying to meet this overall challenge and success.
Yeah, so one of the difficult things about Exascale, right, is there were so many challenges, right? How do you design a computer that's this large, that's this powerful, that's this energy efficient? And so I think that's one of the key reasons in terms of addressing those that we started so early on this, about a decade ago, working together in order to figure out, okay, in order to really meet the mission requirements of the DOE national labs, what types of things need to be done? How do we efficiently design both the hardware and the software in order to work efficiently together and meet the overall requirements for the apps? And then, as we got closer and closer to Frontier being deployed, a lot of these great research ideas move from research into advanced development and then into actual products. And then once the products hit the floor, there's all sorts of challenges in terms of, how do you make sure that you're efficiently cooling the overall machine? How do you get the different components to talk together, et cetera? And we obviously knew how this would happen, but when the machine actually gets delivered, there's the additional challenges of making it all work correctly and work smoothly and as efficiently as possible. And that's where really the collaboration between AMD, HPE, Oak Ridge National Labs, and numerous other institutions was really incredible in helping us overcome those challenges.
With no time on the clock, I'll just reiterate one major point from Mike. I mean, I think Frontier is absolutely, first off, this is John's point, is absolutely something we should all be proud of. And as I'll reiterate, I said before, it's not about the machine. The things that will be done with this machine will be the really impressive things. But really, this is a first of its kind. It is cutting edge. And this type of execution could not have happened without the type of public-private partnership that we've seen between us, AMD, and the federal government. DOE has been an outstanding partner, providing vision and capabilities for us. And these types of successes are going to require this type of industry partnership. And from the HPE side, we're looking to be here, and I'm sure AMD feels the same. We're looking to be here and stand with the US government and our federal partners in the future. Thank you.
Great. Well, we are short on time. Doug, I don't know if you want to end with anything, and then Congressman, I'll give you the last word on our panel. But Doug, I don't know if there's anything else you want to add before that.
Hey, stay tuned for some incredible solutions that are going to roll off Frontier. We're ready to go.
Good. Thanks. Congressman?
Thank you again. I'd like to associate myself with Doug's comments and just please remember, as we go through the appropriations process, investment in supercomputing is critically important. We knew this over a decade ago. We've seen a great progression as we've moved from petaflops to exascale, and the future is bright. And I look forward to the accomplishments of this computer and beyond. So thank you very much, and it's been a privilege to join you today.
Great. Great. Well, I'll just close by thanking everyone for joining the panel today. Thank all our panelists for being here. It was a great conversation. As a kid of the 80s, I still remember my speaker spell and my TI 99 computer. We've come a long, long way from there. So it's exciting to see, how everything is progressing and what we're all doing. So, as I said in the beginning, this is a great example of why TFAI exists, the partnership between industry and trying to, and academia to try to push forward research funding. So thanks everyone for joining, and until next time, thank you.